Dear students, welcome to the knowledge series. Here we are going to discuss on Dijkstra's algorithms shortest path numerical problem. You can view that Dijkstra algorithms shortest path with respect to one network is shown where you can witness nearly 6 nodes with respect to the starting and the destination node. Of course, it is not been highlighted, but you can try to visualize and able to guess which is the starting node and the destination node, over which you have to find the shortest path. Now, if you see over here, looking into the arrow aspects from this node, that is the node P, or the vertex P, all the arrow is emerging out, but rest other nodes, you can see that in certain vertex at least one or two arrows are coming inside, and in certain case it is emerging out also. So based on this, we can we will be confident to say that P is the starting point, and with respect to the rest of the nodes where you find all the arrows are coming towards that node, that terms as a endpoint or the destination. So how we will apply the Dijkstra algorithm to solve this one? So there are certain steps. We will put the step 1. Step 1 to solve this one, first of all we will consider the two factors. What are those two factors? In the in my previous video series, you have seen that we talked about weight and cost. So we consider the link section as cost, and all the respective vertex will have its own weight. Okay, those things we will see. Now, in the step 1, let us see the distance from P and the vertex of P. Every starting vertex will have its own weight as 0, and with respect to P, let us see which are the neighboring vertex which is having a direct contact. So you will find that with respect to the P, Q, S and T, there are 3 arrows which is emerging out of P, and it is going to the neighboring vertexes, that is Q, R and T. So we will write distance from distance of P as a starting point, that is equal to 0. Distance of P to Q we can state as 1. And what about P to T? P to T we can state it as 7. And P to S, it is equal to 6. These are the 3 things we can able to see. These are the direct path, or we can say that the link that exists between the peer-to-peer conditions. There are other links which we consider as an indirect path, that is we will consider P to S, P to R, let me say put as P to R. P to R is having a no direct path, so that's why its weight is infinity. And P to U, which is also a indirect path, its weight is equal to infinity. That is the step 1. Now we will go to the step 2. step 2 onwards, we have to see that we are following the conditions, that is the conditions on relaxation conditions. Relaxation condition. What is the relaxation conditions? If you try to recall, we have mentioned that the next node, its weight will be based on the condition that the previous node and the previous node's link, if its entire weight is lesser compared to the present node weight of the destination, then it need to modify, otherwise it will be the same. That is what the relaxation conditions is being. So based on that, we will find with respect to the rest of the nodes. So we have got the new nodes weight. Let us put those new nodes weight across this place. So here we got it as P2Q as how much? It is 1. And here it is, we got it as 6. Here we got it as 7. Here it was infinity. In the step 1 we have got, and here also we got it as infinity. Now we go to the step 2. In the step 2, let us start among these three. And if you see the all other nodes, the smallest weight it appears for the vertex Q. So we will consider Q is the point over which we will consider the shortest path, and from Q 2 links are emerging out, that is Q2S and Q2R. So we will check with respect to Q2R. So what is Q2R with where P is the starting point, that is the PQR. So PQR, it indicates that weight of Q, that is this that is equal to 1 plus the distance between the Q and R, that is the link cost, is 1. So that is it shows the weight at R is equal to 2. But actually weight of R as per relaxation condition is in the initial period it was infinity. So we have to do a relaxation. That means we have to modify the R with respect to 2. So what we will do, we will cancel it, cancel the previous weight, and we modified this one as 2. So that is the new weight of R. Now we go to the next segment. What is this one? PQX. S. PQS. So in this PQS, what is the weight we see? That is 1 plus 4. That is equal to 5. And what was initially? It was 6. So we have to do relaxation condition satisfy. So based on this, we update to 5. Now we will continue this particular process. Now in this in both the case, our Q weight was small. Okay. Now we go with the next. Now we got here 1, 2, 5, 7 and infinity, where we find R is the smallest one. So we go with the next case R. So if we are considering, then under that particular case we are PQ R, and from R how many weights are emerging out? S and U. So with respect to that R, we will consider PQ R and S. That is one case, and the second case is PQ R and U. This case where we find that R is smallest weight. Under this particular case, what was up to PQR, what is the weight? It shows the weight at R is 2. So 2 plus 2 is 4. So we have 2 plus 2 is equal to 4, which is less than 5. So we update this 5 by 4 with the new weight. So that is the new weight, where we let me put it this one, 4 is less than 5. So that's why we have to update. Now here also we are in this case also 2 was less than infinity. That's why it was satisfied this particular case. Okay, so this is at yes. Now when we consider P, Q, R and U, in this case what is the new weight, or what is the weight? Let us see. 2 plus 1, that is equal to 3. 3 at U. 3 at U is less than infinity. So in this case also it is going to be modified because satisfying the relaxation condition. So this has updated with the new weight, that is 3. Now we have visited P to Q, R, and now what is the next one? We have to see S, U and T. Among this one the smallest weight is U. So we will see the U. But in the U, when we consider U, you will see that under this particular scenario, no link is emerging out. Every ring is tending towards U. So under that particular scenario, we cannot do any shortest edge, and we do not have any edge going out. That's why we leave this particular state. Now we go to the next. So rest is between S and T, where S weight is small. So we go with S, and what is from S, we are going to see from S our next weight is going to T. So S to T is what? It is 4 plus 3 is 7. So if we are considering the next state is what? Again we can put it as S to T. S to T. If S to T, what is the weight? Already this is 4S plus 3 link between the S and T, that is equal to 7. So this 7 is same as the same weight which is existing in the T. So there will not be any change. So no change exists. So finally what we have seen, finally we are seeing a different weight distributions as we say that all vertex are labeled. That is one. Next is that P to R. It is 2 in weight, and it is coming from Q. P to R is coming via Q. And next is what? P to U. P to U is how much? It is 3, and it is coming via Q and R. Okay, then P to S. P to S is how much? It is 4, and it is coming via what? P, Q, R. And P to T, that is equal to 7, and it is a direct path. So these are the path for the shortest distance. If a vertex P want to go to U, then the vertex will follow which is the best path is that you have to see what is the maximum up to R. It is 2. So 2 plus 1, 3. So that's all. If it follows via T, then it will be it is 7 plus 2, 9. So 9 is greater than 3, no change. So it will be this path is not considered. rather the path this one is considered. So this solves the numerical problem related to the Dijkstra algorithms, as you can view here. Thank you.